Welcome to the latest explainer in our finite byte series Beyond the Textbook. Okay, let's just dive right into this. If you open up pretty much any introductory computer science textbook, they're going to tell you that a string is just this simple text variable, a basic container for holding characters. But if you're actually engineering high-throughput backend systems, well, that assumption completely falls apart. The reality is that the Java string is this highly engineered, incredibly complex component that has a massive impact on both your memory footprint and your application security. So today, we're going to challenge those textbook basics and completely deconstruct how strings actually operate down at the machine level.
To pull this off, we're doing a layered descent straight through the JVM. We're looking at security invariants, the constant pool, bytecode evolution, compact strings, and finally, JIT lock elision. All right, let's kick things off with part 1, immutability and security invariants.
So we've all been taught that strings in Java are immutable, right? But I want you to realize this isn't just some convenient syntax feature. It's actually a rigid, non-negotiable architectural constraint. Just think about the terrifying scenario of what would happen if a string mutated right before execution. Strings are our primary vehicle for passing sensitive arguments, file paths, network URLs, database credentials. If a string were mutable, it would wide open the door to a devastating security exploit vector known as TOCTOU, or time of check to time of use. Imagine a malicious thread passes a string with a totally safe, validated file path to a security layer. The layer approves it, but then, right before the operating system actually opens the file handle, that exact same thread mutates the underlying character buffer, so it points to a restricted system file. Well, because the string is immutable, this entire class of access control bypass is structurally impossible. The JVM guarantees that the data checked is the exact data used.
And this immutability actually yields a massive performance side effect. Because a string's underlying characters can literally never change, its computed hash code is permanently fixed. So the JVM brilliantly takes advantage of this. It caches that computed value inside a private instance field called hash during the very first call to hash code. Every single subsequent invocation just bypasses the calculation entirely and hands you back that cached integer. This is exactly what allows string lookups and indexing structures, like HashMaps and hash sets, to operate in blistering O(1) constant time.
Moving right along to part 2, the constant pool memory architecture. Let's examine the heavy machinery that JVM uses to store and share these objects. Because strings are reused so often, the JVM attempts to deduplicate them in the string constant pool to save heap space. But historically, this caching mechanism was actually incredibly dangerous. Prior to Java 7, the string constant pool was isolated inside the permanent generation, or PermGen, memory space. PermGen had a fixed maximum size and was notoriously ignored by the standard garbage collector. So if your application dynamically cached too many strings, say you were parsing user inputs or chewing through large XML files, you would routinely trigger these fatal application-killing out-of-memory error crashes. To solve this, from Java 7 onwards, they completely overhauled the architecture. They migrated the string table directly into the main Java heap, which meant those dynamic pooled strings could finally be safely garbage collected just like any normal object.
Okay, so the crucial point here is understanding how this table is actually built. Under the hood, the string pool is implemented natively inside the JVM as an open-chained hash table of fixed-size buckets. But by default, this table is completely untuned. If your application loads millions of distinct literal values, you're going to suffer from bucket chain collisions, and those fast O(1) lookups will severely degrade into O(n) linear searches. And that brings us to a really cool senior-level optimization secret: the JVM flag -XX: string table size. By manually setting this to a sufficiently large prime number, something like 999,001, you basically force a uniform hash distribution across a much wider array of internal buckets, heavily protecting your lookup latency under massive loads.
Now, it's really important to realize that your code syntax dictates exactly how that memory pool is utilized. When you assign a literal, like string s1 equals EPAM, the JVM searches the string table. If it's already there, it just reuses the reference. But if you type out new string, you are forcing an explicit, brand new object allocation directly on the standard Java heap. You completely bypass the cache and create a duplicate character data snapshot sitting in memory. Finally, calling .intern on that duplicate programmatically searches the pool and actually swaps your duplicate heap reference out for the shared pool reference, allowing the garbage collector to come in and sweep away the wasted duplicate. So remember, syntax directly dictates memory routing.
Let's jump into part 3, bytecode and string concatenation. So what actually happens when you use the simple plus operator to combine strings? Well, the answer to that has drastically changed to optimize runtime resources. For decades, pre-Java 9, the compiler handled concatenation by secretly injecting these explicit string builder instantiation chains. If you added 3 variables together, the compiler hit a new string builder, appended the variables, and then called toString. Now that's fine for a single line, but if you did this inside an iterative loop, you were repeatedly allocating and destroying short-lived string builder arrays and internal character buffers directly on the heap, which absolutely choked the garbage collector. But in the modern Java 9 and above paradigm, this was entirely ripped out. It was replaced with the invokedynamic instruction utilizing a bootstrap method called string concat factory. Under this modern dynamic approach, instead of the compiler hard-coding a static concatenation strategy, it simply leaves behind a blueprint, a recipe descriptor. At runtime, the JVM reads this recipe, looks at your specific platform architecture, and pre-calculates the exact aggregate byte size needed for the final combined string. And then, it makes a perfect, single atomic memory block allocation. 0 hidden loops, 0 intermediate buffer resizing penalties, just pure, highly targeted execution. Down into part 4, compact strings and memory layout.
Let's look at how this all builds into the byte-level memory layout itself. Because honestly, for a long time, the JVM was silently wasting massive amounts of your RAM. Prior to Java 9, every single string instance stored its characters inside a char array encoded in UTF-16. This means every character strictly consumed 2 bytes, or 16 bits. But standard Western alphanumeric text, basic ASCII data, only actually requires 1 byte per character. So for standard text, every alternating byte in memory was just filled with 0 padding. It was literally a 100% memory overhead waste. To fix this, Java 9 introduced the compact strings layout, changing the internal storage from a char array to a much simpler byte array and introducing a brand new dynamic marker field called the coder.
This coder field is a real game changer. It dynamically dictates the layout strategy at runtime. If it detects only single byte characters, it toggles the coder to value 0, utilizing Latin 1 encoding. This instantly slashes your string heap consumption by up to 50% because each character now only consumes exactly 1 byte. But if the string happens to contain multi-byte characters, like emojis or non-Western alphabets, the coder disgracefully falls back to value 1, allocating 2 bytes per character under UTF-16 to preserve absolute data precision. It's this highly intelligent dynamic memory compression happening entirely behind the scenes. Finally, Part 5, JIT compilers and lock illusion optimization.
We have officially reached the deepest layer of our descent today. When you're combining string fragments manually, you generally have to choose between string buffer and string builder, and that choice completely dictates your processing boundary. String buffer is a legacy component all the way from Java 1.0. It is completely thread-safe, but it achieves this by guarding almost all of its operations with explicit synchronized blocks. This forces continuous, highly expensive CPU monitor acquisitions and thread locking overhead. String Builder, which was introduced later in Java 5, is a direct replacement that is stripped entirely of those synchronization blocks. It provides vastly superior single-threaded speed, but because it's not thread-safe, you have to make absolutely sure it remains strictly confined to your local method stacks.
But right here is where the silicon-level magic actually happens. Let's say you're working in an older codebase that heavily utilizes the slow, synchronized string buffer, but you are safely using it within a local method. Well, modern JIT compilers perform a deep inspection called escape analysis. If the compiler can actually prove that your string buffer instance cannot escape the local thread scope, meaning no other thread could possibly access it, it triggers an optimization called lock elision. The JVM actively intervenes and just completely strips the heavy monitor acquisition logic out of the compiled machine code. It dynamically rescues legacy code from performance degradation right at the processor level. It's absolutely incredible. So what you should really take away from this entire explainer is that java.lang.String is far, far more than just simple syntax. It represents a dynamic memory layout, dynamic bytecode generation, and dynamic CPU workload management. Truly understanding this architecture is exactly what separates basic coding from writing optimal, high-throughput backend systems. Before we wrap up, I want to pose a question to you. Have you ever actually had to manually tune your string constant pool cache using JVM flags in a live production environment? Or maybe you've had to investigate an out-of-memory error that traced straight back to heavy string operations? Drop your experiences in the comments below. I'd love to read them. Keep building, keep digging beyond the textbook, and I'll see you in the next explainer.